No, yeah, we are live now.
But can you see my video?
No, I don't see your face, unfortunately.
It seems to come and go as it pleases.
One thing you can do is you can put your presentation later. Just let me introduce you. Let's stop in a few minutes.
Okay, no problem.
Okay, turn off the presentation.
Oh, I can see it now on YouTube. Fantastic.
Do you want to turn off the presentation for a minute?
What would you like me to do?
Just turn off the presentation for a minute.
Turn it off.
Stop sharing the desktop.
No, stop sharing. Okay, sure.
Yeah.
Just 1 minute. Do that. Stop sharing. Okay.
No, I can still see your presentation.
Okay.
Yeah, I can see you now. Okay, perfect.
Oh, I see. So it doesn't show me. It doesn't show me when I'm presenting.
Right.
Oh, that's cowardly. That's really cowardly.
Okay, so let's start. Hello, everyone. How are you doing? Welcome to another JackBD session. I know we all came from vacation, and I'm sure everyone started to come back and with a fresh enthusiasm. So let's get started. Today, I'm joining with Dr. Heinz Kabutz. He writes the popular Java Specialist newsletter. I'm sure many of you already subscribed to his newsletter. If not, do it now, or maybe you can do it after this presentation. Hello, Dr. Heinz. How are you doing?
Hi, Puzzler. Thanks so much for inviting me to speak to you guys. And it's really a great pleasure to be here. I told my wife that I'm speaking to some people in Bangladesh. She says, "Oh, send my regards to the Indians." I said, "No. This is Bangladesh." She says, "Oh, yes. And she thought it was a city in India. And I think a lot of people in where I come from think that Bangladesh is just a city either in Pakistan or India. But of course, we know better.
Right.
So that's of course not the case.
Yeah.
Thanks for having me.
Warm welcome from Bangladesh.
Thank you very much.
You live in island of the Crete, I think. Tell us a bit about it.
Okay, so I am originally from South Africa, and where we play cricket. I know you know cricket, and we moved to Crete, the island of Crete in the Mediterranean Sea, about 12 years ago. And what I do is I travel the world teaching advanced Java courses and speaking at conferences, but I do the conference talking for fun. That's really just entertainment to keep myself busy. And I keep myself busy in doing different things like that, programming, and I try to specialize on concurrency and multi-threading and parallelism. That to me I always find it interesting and fascinating. So I think it's important when you are doing something that you find it interesting. Otherwise, you stop. You don't work as hard if you're slightly bored with what you do.
Yeah, that's what we do. In fact, we all here Java enthusiastic, and definitely the work you've done is part of the Java. So would love to hear from you. So before starting the presentation, I would like to tell the audience that Dr. Heinz is a performance specialist. He is an expert in concurrency and JVM. So you can ask any question if you like. He hopefully will answer the question regarding anything, concurrency, JVM, and the topic as well. So let's start. Let's get going.
Well, I can answer any question you have, but the answer might not be correct, or it might be I don't know. But I'll give it my best shot. Yeah. I'll try my hardest to get it correct.
Right.
Just start the presentation.
You can start your presentation now.
All right. That's the wrong button. Wrong button. Okay, let's go here. So we're going to look at doing some coding to parallelize some existing code, and we're going to start by looking at fork join, how to parallelize using fork join, and then we're going to look at the ManagedBlocker. That's a little tool that was added with the fork join to allow a better utilization of existing hardware. Now, just to whet your appetite a little bit, this is what my CPU graph looked like before I used the ManagedBlocker. And you can see the cores here at the top left, core 0, 2, 4, and 8, 2, 4, and 6. At the beginning, there's quite a lot of black. And the black basically says that the cores are not being utilized fully. We want to have as much green as possible in the real cores, not the hyper-threaded cores, that don't matter so much. But here we want to have as much green, as little red as possible. And also, if we want to use if we want to utilize our hardware, we want to use have as little black as possible as well. And you can see that most of it is good. So sort of from about, I would say about 14% onwards, it actually became fairly good, except right at the end. But before then, it was the beginning was where the problem was. So by utilizing something called a ManagedBlocker, I made it look like this, where right from the beginning, we were almost 100% utilization for all our cores, and we're talking about 0, 2, 4, and 6, not 1, 3, 5, and 7 that are shown in my task manager view. And to make it even better, we also finished about 8% faster. So the timeline is the same between both of them. Now, as an example that I'm going to use here is the number series Fibonacci, which I'm sure you have seen at some point in your life. And basically, it was invented by someone called Leonardo of Pisa. And it works like this, that you start with 0, the next one is 1, then it's 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and 13 plus 8 is 21, and it just continues like this. After a while, the numbers become very large. And in Australia, they had this problem with rabbits, which started breeding. Someone thought it'd be fun to go hunting rabbits, so they let some rabbits loose, and they bred like rabbits, and all of a sudden there were billions and billions of rabbits until they managed to get rid of them. So the numbers get very large, and also if you have a very naive implementation of this, it's going to be very slow. So here's a naive implementation, and here we write the Java code very much like we would write the mathematical code. So the mathematical definition is f of 0 equals 0, f of 1 equals 1, and then f of n equals f of n minus 1 plus f of n minus 2. And this over here gets slow very quickly because you have to work out the previous numbers over and over again. There's no memory of what you'd had before. And actually, the complexity, the computational time complexity, is in itself a Fibonacci series. So as the numbers get larger, it takes longer and longer to produce the results. And I did a calculation where I took BigInteger, and I estimate that to work out Fibonacci of 1,000 would take something like 10 to the 200 years to complete. So that's longer than we have time for today. So this is another way to try and code it, is to do it iteratively. So we don't want to actually work out everything over and over again. We just want to work out the previous two numbers and then base the next one on the previous two. So it's just an iterative solution, and the iteration is very fast, but the problem is that long overflows quite quickly. So your long overflows after a very short time. So after about n equals, I think, 65 or 6 or 7, it's overflown, and you end up with the negative number, so the incorrect result. So you get a fast result, but it's the wrong result. Now, you might say, well, why don't you just use BigInteger? Well, that's a good idea, but BigInteger's add function is also linear. So the function is linear, the actual function is linear, plus the add is linear, and so you end up with basically it having a quadratic. It's n times m, but we can just say order n squared. So it's basically your bubble sort type of complexity in this algorithm, which means we can work out fairly large numbers. We can work out Fibonacci 100 and 1,000 and 10,000. But we will not be able to work out Fibonacci of 1 billion or 100 million. It will simply take far too long. So here's our third attempt. We could take Dijkstra's sum of squares. So this is what the algorithm looks like. F of 2n minus 1. So if it's an odd number, if n is odd, you add the squares together. And if it's even, you've got some other calculation you do to get this right. Now, the actual algorithm is logarithmic. And until Java 7, the multiplier in Java BigInteger was also quadratic, like the order n squared. But nowadays, it's actually got better complexity. So it's either O(n to the power of 1.585 or O(n to the power of 1.465. And you might say, well, that's not so much smaller than 2, but it's a big difference. It's a very big difference. So that's the first thing we do. And we're going to, after that, we're going to see if we can make it multi-threaded. Because at the moment, multiply is still single-threaded. Even in Java 9, it's also still single-threaded, the multiplier. And it is actually something which one can parallelize very nicely and very effectively. And I'll show you how to do that. So first demo. And the way we're going to do this is I'm going to write a bunch of demos, and then I'm going to check them into my source repository. And you can then have a look at those in your spare time at a later stage. And also, if you haven't signed up to my newsletter, you might find that interesting too. So the first thing we need to do at the moment, Fibonacci test would take, Fibonacci 1000 will take 10 to the power of 200 years to complete, right? And we're going to do it in like a millisecond once we're done with it. So this would just run and run and run with the current algorithm. And we want to make it run a bit faster. So let's do that. Let's go to Fibonacci and implement the sum of squares. Basically, we're going to say int half equals n plus 1 divided by 2. Then we're going to say BigInteger f naught equals f of half minus 1, and f of 1 is going to be f of half. Okay. And then we need to look at the n, whether it's odd or even. So we're going to say if n 2 is 1, so if it's odd, first of let's do the, which one should we do first? Let's do the I think the even one, no, the odd one first. So if it's odd, then it's just the squares. So if it's odd, then we're going to say return f of naught dot multiply with f of naught dot add f of 1 dot multiply with f of 1. Okay. Else, if it's even, we're going to say f of naught multiply by 2. And of course, you know that to multiply by 2, we can simply say shift left by 1 bit, add f1, and then multiply the result with f1 again. And that is going to implement the Dijkstra sum of squares, I think. we'll test it now. And it will be a lot faster than 10 to the 200 years. So let's run it and see how it performs. 5 milliseconds. Okay. And there's no warm-up here, so if we run that a few times, we probably get much better results than 5 milliseconds. Probably get like, 20 microseconds or even less than that. So we have Fibonacci 1000, and we can work out a bunch of different Fibonacci values over here. So let's run this whole test suite, and Fibonacci 1000 is very fast. 10 million takes a bit longer. So 10 million takes like 3 seconds. 1 million takes 82 milliseconds. And 100 million does take a bit of time. Now, what is interesting is if we open top at the main whilst it's running and sort by CPU, we notice that Java is running at 100% CPU. Okay, so that's Java running, and it's basically running with one core because, well, it's a single-threaded algorithm, and so there's nothing we can do to make that run faster. Now, note that we improved the performance from 10 to the 200 years down to like a couple of microseconds. So we've really come a long way here. But we want to also utilize our available hardware to do this faster. Now, I think it's finished now. And we should see that this is completed. Oh, this is long. Normally it's faster than this. I think it's, I think Google Hangout is really grabbing a lot of my CPU power, a lot more than I realized. So, but that's okay, because it's going to be a relative improvement, hopefully, over what we had. So we start with 55 seconds. That's our first time, which is better than a gazillion years, which is what would have been otherwise. And that was our step one. What was that? Okay, now what are we going to do before we go further? We're going to commit that. What are we doing? Commit, say. That's step one. And you can see it's much faster than it was before, but we want to see if we can make it even faster than that. So the next step we can do is to parallelize our code. And we're going to start by parallelizing our algorithm. Now, you notice that we worked out F0 and F1. We could actually run them at the same time. So we could modify them at the same time. And that could be quite fun. And the idea here is what we do is we create a new recursive task. This is a fork join task. And all this does is it calls f of half minus 1. And then after that, we fork it. We then work out the f of half. And then we join with f of 0. Now, if we're lucky, we're going to be able to do it in parallel so that we can actually improve our performance. So let's try that and hope that it makes things better. So we're going to create a recursive task here. Recursive task of BigInteger. F0 task equals new recursive task. And all it does is it returns the code that's over here, f of half minus 1. So f of half minus 1, like so. And then we fork that, which potentially might run it in a separate thread, or it might not. I'm not exactly sure. It's pretty much decided internally. And then afterwards, we say f0 task dot join, like so. Now, I'm actually going to comment out some of these tests because we don't want to run all the tests. I'm going to comment out the 1,000 and the 1 million and the 10 million. And we're just going to run the 100 million because that's the one we're actually interested in. So let's run it again. And now we should see some parallelism. See, there's Java running at like 500%. Okay, but after a while, it goes down to like 300%, 200%. And it slowly goes down until eventually we're back at 100%. So we started good. We started with it actually running in parallel. And what I'll do is I'll just restart that so you can see that again. Okay, 27 seconds. That's pretty good. But I want to just show that again because I want to have the top there when we're starting. So you'll see it should start with around about 800%. Yeah, so it's like 600%, 500%. It starts very well, and then after not too long a time, it goes slower and slower and slower until eventually it's 100%. And when I saw this the first time, as I started playing with this a while ago, I didn't quite know what the problem was. The first thought I had was that I hadn't actually done the parallelism very well. And after looking at it a bit, now how do I do this? I want to get to the output. After looking at it a bit, I realized that we're spending most of our time in the multiply. And the multiply of BigInteger is not actually parallelized. So this was the third. This is the third step we're going to do. But before we do that, let's commit this again. So we're going to commit step 2. So you can afterwards look at all of the steps that we've gone through in this presentation. Great. Now let's look at demo 3. Demo 3, what we're going to do is we're going to also parallelize the way that BigInteger works. Now, this is something you shouldn't really be able to do, but you can. And there's some very good reasons why it's possible. And you see, it must be possible for the people who are working on the JDK and on the JVM to modify it whilst as versions progress. And so they must be able to patch it, and in order to try out their latest things. For example, when they produce a new concurrent hash map, they want to test it, and they need to do this by patching the existing JVM. So we've had this possibility for quite a long time to add our own hacked version with a boot class path. In Java 9, it's a bit more complicated. I do know how to do it, but it's very involved, and you basically have to create a patch for the module. You can do it in Java 9 too, but it involves 3 steps rather than just a single step. Now, if you look at the multiply within BigInteger, the way that it works is that if the number is very small, they use just a normal multiply. And the reason why is that there's a certain setup cost for Karatsuba and Tim Cook, which you don't want to have to pay if you if it's not necessary, if the number is small. There's like a constant value. There's a constant amount that it just doesn't make sense to parallelize. And that constant is bigger for Tim Cook than for Karatsuba. The setup cost is higher for Tim Cook than for Karatsuba. And because of this, they have certain thresholds beyond which they're going to use Karatsuba. And if it's even bigger, then they're going to use Tim Cook. That's for the largest numbers. So we could actually parallelize both Tim Cook and Karatsuba, but Karatsuba most likely won't have a big effect. So let's try this first of all and see if it makes a difference. We're at around about 27 seconds at the moment. What we're going to do now is we're going to go to BigInteger. This is now the BigInteger from the JDK. And if you want to know how to write lots of lines of code per day, this is how you do it. Control A, Control C. Then we go here and we say Control V. And boom, we've just written like 2,000 lines of code. Brilliant. Okay. But of course, you need to be careful of licensing, because this is now, this BigInteger is licensed under GNU public license, so GPL, with class path extension. Okay, so let's go here. And if you look at the square Tim Cook, this function inside here, you can see that there are 5 different square calls. There's a square over here. There's another square over here, another one there, and another one there, and another one here. So there are 5 different squares. So it's basically recursively calling square. And if it calls square and the number is still too big, it's going to do another square Tim Cook. And if it's still too big and you do another square, it's going to do another square Tim Cook, until we've reached the threshold where instead it's going to do instead of a Tim Cook, it's going to do a Karatsuba. But at that point, it's already small enough that we don't need to worry about doing this, about parallelizing that. So you could parallelize it. It's quite easy to do, but it's not going to win us very much. Okay, whenever you parallelize, you always want to know what's the threshold below which it doesn't make sense to actually parallelize this. All right, so let's do that. Let's do it here too. Here we're going to do this following. We're going to do it as, first of all, let's go back to the correct one, to the changing one, which is this one here. This is what I want to change. So we want to now make a square task, which get my v0 task equals new square task, where we're going to simply square a0. And v0 task dot fork. And I need to define this. I'm going to define it as an inner class. BigInteger A. And we're going to make a field for that. And this is going to say extends recursive task. Now, you've got recursive action, recursive task. I hardly ever use recursive action. I normally use recursive task because it's a better approach for a functional type of programming where you are creating something which returns a value rather than have some global state that you want to change with all the concurrency issues involved in that. So this is what I normally use as recursive task, BigInteger, and then we need the compute function inside there. And the compute function will simply say return a dot square. This is what the recursive task looks like. And I'm constructing it as an inner class inside BigInteger. In fact, I'm going to make this a static class too. I'm going to make another one for the multiply. It's going to be the multiply task, extended recursive task. And I'm going to here have BigInteger a comma b with the constructor. And then compute is going to say a dot multiply of b. So I've basically got two different tasks. Those are both recursive tasks, which allows us to do them in parallel with the fork join pool. So this is pretty cool. Let's go back to the square Tim Cook. Should be sorted here. So square Tim Cook. There's it now. There it is. And we've got the first task, which is V0 task. We fork it, and then we do another square. And before we do the third square, we're going to say V0 equals V0 task dot join. So the way I do it, because other things can get you in trouble, other approaches, is I try to only have one outstanding fork at a time. So I'm not going to fork 5 times and then fork, join 4 times. I'd rather just have a single fork and then a join afterwards. Okay, then I do the same thing for V1. I'm going to say square task V1 task equals new square task of this is for DA1. DA1 over here. And I'm going to say V1 task dot fork, and I'm going to do 2 squares. Once I'm done with those 2 squares, I'm going to say V1 equals V1 task dot join. So I've now forked and joined, and this should already speed things up. We're also going to say multiply Tim Cook. We'll do that here too. Here it's going to be the same idea, except it's going to be a multiply task B0 task equals new multiply task A0 comma B0. Again, you get that from here. B0 task dot fork. And before we do the third multiply over here, we're going to say V0 equals V0 task dot join. And again, multiply task V1 task equals new multiply task DA1 comma DB1. You get the idea now. And the interesting thing here is I actually don't know how Tim Cook works. I haven't tried to figure it out. I don't know how it works, and I don't care how it works. I don't want to know how it works. And I'm parallelizing it, even though I've got no clue how it works. Now I can say V1 equals V1 task dot join. Okay, and this shows you that you can take existing code, you can parallelize it even without understanding anything about it, right? As long as, of course, it's done in a functional programming style. If these methods over here set temporary state, shared state, then this wouldn't work. It only works with code that's already in a functional style. All right, so that's a very important thing. We don't want to have shared state. In fact, shared state is bad anyway. Now, if everything worked, then this should work and give us a good result. But we'll see. Okay, let's try it. Now, you notice now that Java stays at a higher percentage CPU. Whereas before, it used to, okay, it's going to 200%. It's still, yeah, not for such a long time. In fact, it's absolutely no difference. And the reason it's no difference is because we're not actually using it, right? So if you look at the result now, it's still much of the same, okay? It's not actually faster. But we're not using this algorithm. We're not using this BigInteger because we haven't actually set it up yet. So what I'm going to do is I'm going to at the top of this class, I'm going to have a static initializer block using hacked BigInteger, just to know if I'm actually using it or not, because we're not using it at the moment. And I picked it up from top, but you might not know that, right? So it's not using it. Okay, so we know this isn't actually going to help us at all. So to do that, to use it, you need to use the xboot class path. And at the moment, I've got it as just minus xboot class of /a, which is append. It's got to be /p, and then basically a path up to where the binary files are. Okay, so let's run that again. And now we should use the hacked BigInteger. There we go. Brilliant. And if you run top, the Java is now running at a higher percentage CPU, and it should run at a higher percentage CPU until the end, until we're done. Okay, and we're done. So that's fun. And we have improved the time. Okay, come on. So we're going to record that, and we're going to do a check-in. So this is now test. In fact, yeah. So this is the that one. Now, what I want to just do, I'm going to check it in. Get commit -a, and I need to also add BigInteger. Get add mathhack source. I always forget to do that, and then you don't see it in the source code. Okay, this is step 3. What I want to do now is I want to time how long these multipliers take. Okay, so we're going to put a timing in here. Now, of course, to work out the time, you could just say system current time millis. We all know about that. The problem with current time millis is that it's actually quite a slow call. It's a native method call, so it's going to take a bit of time to return that. And we don't really want to wait for that. And we don't want to call it for very small numbers. We only care about big numbers. So what we're going to do is we're going to say, if n is bigger than 1,000, then we're going to do current time millis. Otherwise, we're going to just say 0. Okay? And then I'm going to do it like this. This is sort of my little trick for finally. To try finally, I'm going to say time equals, if n is bigger than 1,000, it's going to be system.currentTimeMillis minus time, otherwise just 0. Okay. And then we're going to say if time is bigger than 0, bigger than, let's make it 50. We don't care about very small numbers. Print out if percentage d hook, percentage d, percentage n for new line. This is for the n, and then we have the time in milliseconds. Right. So now when we run it, we're able to see how long each of these take. Okay. If you look at these numbers going past, do you spot anything? This is normally where I get interactive with the audience. Do you notice anything? Look at this.
Right.
So some numbers are being calculated multiple times. So this one is like this one, for example, which is or this one, 1, 2, 3 times.
Yes, few are computed multiple times.
Yep. So let me just check that in because I think that's quite an interesting little step to have in there with timing. And let me show you this slide here. So what I did was I took 1 million and I tried to work out how many times, what are the different numbers that we need to calculate in order to get to 1 million. So the way that the Dijkstra sum of squares works is you're going to work at 1 million, you need to work out 499,999 and 500,000, right? And to work out 499,999, you need to work out 249,999 and 250,000. Is this correct? Yeah, that's right. And this one actually has to work out the same ones to work out 500,000. Now, of course, the calculation for combining them is different. In this case, you're going to say square of that plus square of that. And here you're going to say this multiplied by 2 plus that multiplied by the one on the right-hand side. So, but the foundation, the actual number we use to calculate this is the same on both sides. To work out at level 5, 31,000 needs 16 times. You're going to have this number calculated. And this goes all the way down. So for level 14, for example, you're going to have 60 times working out Fibonacci of 7,904. So there's a fair number of redundancy with this numbering, with the numbers that are being worked out. And that's the step for the step number 4, where we're going to cache previous results. Now, there are a couple of things we've got to be careful of. The first thing is we don't want to have a memory leak. And we don't want any static maps. Static maps most have got a very high chance of causing memory leaks. So this is demo number 4. Inside our calculation here, we're going to now have 2 different f functions. The one is the old one, and then we've got a new one as well. So the old one is going to, sorry, I'm getting confused myself here. So the old one is going to just be the public one. Then we've got a private one here, which is going to also take a map from integer to big integer for we'll call this the cache. Now, the cache, unfortunately, is going to have to be a thread-safe cache. Now, you could use a hash table, but hash table is not the best in terms of concurrency. So we're going to say map from integer, comma big integer, cache equals new. We're going to use a concurrent hash map. That's the fastest way of doing this. Concurrent hash map is very fast at reading. It's not so fast at writing, or it's not necessarily fast at writing, but it's for reading, it's very fast. We're also going to seed it. We're going to say cache.put 0,0. And by the way, in Java 9, they now have 2 as well as a predefined value. One of the small changes. And 1. Okay, 0 and 1. And then we're going to say return f of n, comma, cache. Right? Now, inside here, we're going to change this a bit. We're going to say, first of all, big integer results equals cache.getN. If results is null, then we're going to do all of this stuff. And when we say return, we actually need to say results equals and results equals. And at the end, after the if statement, we're going to say return. Okay. Now, we also have to, of course, call f of n comma cache, so calling all the correct functions. Now, hopefully, if we've done everything correctly, it's going to pick up the values from the cache rather than work them out over and over again. And this should decrease our time taken to calculate this. All right, let's try it out and see whether it works. You might look at this and wonder whether it's working at all, because we still have the same problem as we had last time. In fact, we've made it slower. And right now, I'm actually wondering about whether that's working at all myself. Maybe I'm not putting it in. Yeah, you see, I'm not putting it into the map. So it's not actually working. Let's over here say cache dot put n comma results. And now we're going to try it again. Hopefully, it's going to improve things a bit. You'll still notice that we're working out some values twice and 3 and 4 times. Please be faster. Now, it's slightly faster than the previous run, but it's not as fast as the other run we had. So I'm now at a loss whether it actually did anything or not. I don't know. Did it do anything? Good question. What we'll do is, let's see what we do. We'll make the cache dot get. Okay, so what we'll do is, if result is not null, we're going to print out found results for n equals n. So actually see whether we're going to see the results, whether it's working, whether it's actually finding the results. So it's finding the results over here, as you can see. But it's still working them out multiple times. Okay. So this time, for some reason, we were lucky. And that's sort of the time I was expecting to see. It's difficult to get any performance values here because I'm running the webinar on the same machine, which is kind of a silly thing to do. But this is a more likely answer. I'm going to actually put this in here. And I'm going to keep this one 4. Okay. But we still have the problem that some numbers get worked out multiple times. This one, for example, this one gets worked out multiple times. All right. So I'm going to run it once more just for fun. I'm going to take out this print line. I don't want to show this. And run it once more and see what the result comes out as. Now, there will be some duplicates, we know that. And to explain why they're duplicates, I can show you this diagram again that we had, which shows you that there's actually a very high probability of having multiple threads trying to work out the same number at the same time, because it's always on the same level. So you're not going to have one, because we're parallelizing, they're all sort of working at the same level at the same time, and most very likely chance at least. So what will happen is that they both come in there, they both see that it's null, and they both try and work it out. Now, the obvious way to solve this, okay, now it's 13 seconds, so I'll keep the good one, the 12 seconds. The obvious way to solve this is to use compute absent instead of get. So instead of saying cache.get, we can say, I'm going to just copy and paste this. Is to say cache.compute_absent in comma. Now we have a lambda which actually does the calculation, because that's really what we are doing here. In fact, I don't know if they recommend it automatically. Pick it up. No, they didn't pick it up. So I thought maybe they picked it up. And so this is sort of the obvious thing to do, is to say, well, let's use compute if absent to do this. So we don't have to say put, and this way only one thread will actually get a chance to only one thread will get a chance to do the calculation. Okay, and then we need to close that. We have to close that, and close that, and close that. And that's going to be return. So we're going to just say here return. So this sort of is the way that you think it should work. So just say compute if absent. Except it does not work. In fact, it doesn't work at all anymore. Now, if you run this, it's going to die a horrible death. Even test 1000 doesn't complete. We've got an infinite loop inside concurrent hash map. And the reason why it doesn't work is because we are modifying the structure of the table inside this calculation. So this is a particular use case you're not allowed to do with the concurrent hash map. Not allowed to change the structure of the table. Let me just go back to the result we had. So that wouldn't work. We can't use compute if absent. What we can do is we can implement a scheme where we say, instead of just, have I actually checked this in? I don't know. Have I checked it? I'm not sure now. No, we haven't. Okay, we'll just check it in. What we can do is we can have a scheme where we say, instead of calculating the same value twice, let's put a special placeholder into the map to say that we want to work this out. And we can do this with put if absent. Now, if put if absent comes back with a non-null value, then that means that if it's the placeholder, then we wait until something else is finished. But if the result that comes back is null, then we were the first to put the placeholder into the map, and we can start working immediately. So it's just like putting up my hand saying, hey, I'm going to do this now. I'm going to calculate this, and then in the meantime, anybody else who comes along will have to wait. So before I do that, let me just check it in. 4. Yep. And let's implement this. So let's make a special value. So it's going to be private final big integer, put it reserved, equals big integer dot value of minus 1,000. Some value. I'm going to make it a negative, just to differentiate that if I want to know is this reserved or not, I could just see if it's a negative value, then it would be reserved. And then instead of saying cache.get, I'm going to say put if absent in comma reserved. Now, if it comes back as null, then I know that I was the first to put it in. Okay. So I must do the work. I must do the work. Okay. If the result, else if result is reserved, that means someone else is busy with this number. I'm going to wait. I'm going to wait until they're done. Okay, so the waiting here, we're going to say synchronize on reserved, and we're going to say while results equals while results is equals cache.getN is equal to reserved. As long as it's still reserved, we're going to say reserved dot wait. Now, of course, as we normally do, we end up with an exception here. The corrupted exception, which we're going to simply say throw new cancellation exception. That's going to be that we were interrupted, which means we're going to say we can just cancel this particular run. But we're going to keep on reading the result whilst it's reserved. So whilst cache or get comes back as reserved, I'm going to wait until eventually it's not reserved. In that case, I'm going to return the result. Okay. This is the waiting part. It's fairly easy to do. And then in the other one, which is the actual construction, once I've put it in, I actually want to wrap this with a synchronized as well. Reserved. I'm going to say reserved dot notify everybody. Anybody who's waiting must be woken up, and to say that it's now ready. And we're going to run this and see if it improves the performance. One thing which it should do is that we should only see every number a single time. So that we can easily verify. You can see here that each of the values is only worked out a single time. And we've improved our performance too. You see? By not doing unnecessary work, we've improved our performance. Now, of course, we have actually introduced a possible contention here, but at least we have made it faster. So we've gone from 55 seconds down to 9.9 seconds, just under 10 seconds, with a few bit of hacking. Of course, the biggest win we got so far was from improving the algorithm, which we got from 10 to the 200 years down to like 5 milliseconds. But you know, at least we are now using some of the parallelism that we've got available. Any questions? I've got one more.
No, not yet. Hi.
Okay. Good. Let me quickly commit that.
Sure.
There's a step. What's going on here? I've changed my keyboard to Greek. That won't work. Okay, step 5. Right. So the last step is this. So the problem that we have with the current system is that whilst it's working, there are going to be some threads which are blocked waiting for work, waiting for other threads to finish their work. And it decreases the parallelism of your fork join pool. Up until now, it's been quite difficult to configure the fork join pool in any way except for, all you could say is, how many threads do you want to run at the same time? So in other words, what's your desired parallelism? So the only way to do it, and by the way, we're always using, in all my demos here, I'm using the common fork join pool. If I say fork join pool over here, I've got three constructors. So one is with no parameters, which takes the number of hardware threads minus 1, or maybe the number of hardware threads, actually, I think it does. It uses available processors here. Okay, so just as on my machine, we'll have 8 threads. Or I can specify a number like 4, 16. In Java 9, there is another constructor that they've added. I discovered that on Thursday or on Wednesday. We can say fork join pool, and you can now specify core pool size, maximum pool size, minimum runnable, and then a predicate for saturation, keep alive time, and a time unit. So it's become more configurable. So you can actually say that I want to have a certain number of core threads which always stay there, and I want to have a maximum number of threads which won't go more than the maximum. Up until now, up until Java 8, this has not been possible. In Java 8 and before Java 8, you couldn't actually configure this any more than just how many threads do you want to run at the same time. And that's what we call the desired parallelism. Parallelism. I really struggle to say that word, parallelism. Now, the number of threads you've got in there is normally the number of hardware threads, because fork join pool is typically used with CPU-intensive tasks. Now, what you can do is with the managed blocker, you can say that if one of the threads has to block, a new thread can be started to take its place. Now, this is done with a thing called ManagedBlocker. And we use this to keep the parallelism high. So let's try that out as well. This is now the last demo, and then I've got one for homework for you to do. And this one, we're now going to create a reserved blocker. That's going to be, let's call it Fibonacci blocker. A private final class Fibonacci reserved blocker. Implements managed blocker. Now, what this does is it basically encapsulates this statement over here, this try and sleep. I'm going to just move the code around a little bit, put this in there and put this in there. I'm going to just move the synchronize into the try catch, right, like that. And so this Fibonacci reserve blocker, it basically encapsulates this block of code that's up here. Okay, that's what it does. And we're going to need to do this. We need to, first of all, n. We also need the cache, final map of integer, comma, big integer, cache. And we also need a reserved, which we're going to use to pass, results, which we're going to use for passing the result back to the caller. Okay, so let's add the constructor with n and cache, like so. Then we've got two methods. The first one, I'm going to put is releasable first. The first one is basically your condition predicate, right? What it is. And the condition predicate is this over here. That's your condition predicate. So it's going to say, is it releasable? Well, is the result not equal to reserved? It's the opposite of the other one. It's basically, if it's releasable, then we don't have to block. We don't have to worry about blocking because we've already got the result in our hand. And you could also here say, return result is not equal to reserved. Or in fact, it's not equal to null. And I'm just wondering if that's right. No, it's not equal to reserved. But you could do this. You could say, well, if I've already read it, I don't want to read it accidentally into the result a second time. I don't want to call cache.get if I've already got the value. In our case, it doesn't matter if you read it twice, because when you call cache.get, you're going to get back whatever's inside the map. And that doesn't change until you finish with the call. So in our case, we don't need to worry about this, but in other algorithms, you might need to make sure that is releasable is only called, or that you only read the values into your local variables or into your fields if you haven't done so before. Let me take this away because you don't need it in our case. And then the blocking would basically be this code over here. So that's this. I'm going to copy and paste this down to the bottom. And we're going to say synchronize reserved, whilst I'm going to say is not releasable. We're just going to say reserved.wait like that. And then lastly, we're going to say return true. Whilst not is releasable, reserved.wait, and then return true. So keep on waiting until it's releasable, and then we exit from there. Now, to use it, we're going to say reserved Fibonacci reserved blocker. Blocker equals new Fibonacci reserved blocker. We pass in the n and the cache. We're going to say, now we're not going to say blocker.block. Could say, but that wouldn't help us make it faster. We're going to say instead fork join pool dot manage block and pass in the blocker. Fork join pool internally now says, wait, if I don't have enough threads running, I'm going to construct new threads to pick up the slack. So it's going to manage this blocking that's happening. And then result equals blocker dot result. This can't be null, it can't be negative, and it can't be the reserved value. If it was, that is a mistake. We could say assert results not equal to reserved. It shouldn't be reserved, and assert results is not equal to null. Okay. So we're sure that it's not. We know it can't be reserved or null. Let's run this again, and this time you're going to see, hopefully, a better utilization. Okay. Now, it's a bit hard to see because actually let me try it again. It's as I said, it's incredibly difficult to do this presentation whilst other stuff is running on the machine, because Google Hangout is not insignificant. You can see there's a slight improvement, not enough to really get excited about, and which makes me wonder, is it actually using it? So the way to test that is to run it and to generate a stack trace. Okay. Now in the stack trace, if it's using it, you're going to see, if you search for common pool worker, inside here, you can see that we're going to have numbers here which are bigger than 7. Okay, so it is constructing additional workers to pick up the slack. 19, 18, 8, 13, 14, 12, 11, 0, 7, 6. The total number of workers should add up to 7 workers, because we also use the main thread for the calculation. Let's start again. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we've got a few which are blocked, which is why it's got a few more threads running. So it is doing what it's supposed to do. It's probably going to be slower now, slower now. As I said, this demo doesn't work very well when there's other stuff happening on the machine.
I think Hangout is taking a lot of CPU cycle.
It is. Here we got a good one. Thanks. Just Buzzlord, just keep on speaking. That seems to help.
Yes.
So this was the last one we did with ManagedBlocker. Okay.
Okay.
I knew I had to run it a few times, so it's gone. It's like 10% better. And if it's a bigger number and you've got more cores, this actually makes a big impact, because where you're improving it is at the beginning of your calculation. You're improving it. So this was our final little hack here.
I have really a question about this improvement. This is not really related to rather garbage collectors. We know we have a different type of garbage collectors: CMS, serials, parallels, and G1. In fact, so is there any way to changing the garbage collector and improving a little bit? I mean, we are creating a lot of objects here also.
Yeah, so that's interesting. What I'm doing is I'm actually doing a parallel calculation with as many threads as possible. So using CMS or G1 is not going to help us that much. Azul will also not help us that much, because Azul is really for to improve the young generation. That's where it really will shine. Okay. What you might have noticed, I don't know if you paid attention to that or not. I'm going to just quickly run it. In fact, let me just commit this, because before we go further, step 6. Okay, so when I ran it, I had a bunch of GC things here. Okay. Let me take them out and run it without that. Not my GC settings. So just the standard out of the box GC. Without any tuning of the GC. Oh, it was faster. Okay. I thought it'd be slower, but for some reason there's actually, but it's very hard, as I said, it's very hard to actually be conclusive about that, whether that makes sense. So yeah, I have in the past done tunings of this to improve the performance. I don't think that G1 would make it faster. Again, it's not going to be very helpful to, let's just try it, minus X. Use G1 GC. Just obviously straight off the box might not be the best performance. The thing is, you're going to work with humongous objects here. They're very large. So G1 does struggle with that a bit. Yeah, didn't do too badly. Wasn't too bad. This isn't really a program where you're going to use GC. That's what I meant, yes. There are many other examples where you're going to get where you need to do GC tuning. We do GC tuning all the time, but this is just number crunching, do it in parallel.
I have actually
all very similar.
Okay, sure. I have actually related question to this. In fact, so we are using fork join framework for this particular problems. I mean, crunching the numbers. So, is there any criteria like for this particular cases we're gonna use this fork join pull framework? Otherwise, we'll do like we had previously executor service and other stuff. So, is there any criteria like if the
Sure.
work size is this, so we have to use the fork join framework to solve this, and it will improve the performance dramatically. Otherwise, we can use the executor service like we did earlier before the fork join frameworks came.
Okay, I got it. So let me explain that. Your fork join pool is for parallelism. That's the purpose of it. The executor service is for concurrency. So these are two different things. So, for example, if you've got a network service, you want to use the executor services. But any sort of parallelism, like if you want to do some parallel work on a collection, for that to use the fork join pool, which is of course used by the parallel streams. The parallel streams internally use the fork join pool, the fork join framework. So
right.
you would use it whenever you want to do a divide and conquer, recursive decomposition type of algorithm, or if you're doing manipulation of data structures. With that also, you want to use the fork join pool parallelism, because it's quite easy to parallelize that usually. Right. But any sort of blocking code, if you've got a network service, disk IO, you want to also do that with executor service. So the fork join pool is actually an executor service, an executor, not an executor service, an executor. Or maybe it even implements executor service. In fact, it does implement executor service, but it's not the thread pool executor. It's got different purposes. All right, we've actually reached the end of this. I've got one more slide, which is your homework. And that is, you need to do some homework. You need to figure out how to do this using completable future. And some tips you can use, then accept both async and complete. And you can try out what happens with your thread creation if you disable the common fork join pool. That's a very interesting little, should we say, feature of the completable future. But this is beyond the scope. If you want to, you can send me the answer to my email address, heinz@javaspecialist.eu, or just say hello and say you enjoyed it or didn't enjoy the talk. And as I said before, thanks very much for inviting me. If you find this useful, subscribe.
In fact, I actually wanted to ask about quotient, the computable feature, but you put that in homework, so I guess we have to do it.
That's homework. That's homework.
I had this question in my mind when you were doing this presentation. That's okay. So lastly, one question, just it's not related to this presentation. However, I see the technique you presented here is quite a complex one. I mean, not that everyone will be able to grasp it with it. I mean, a lot of freshers here in our community, so I'm sure they will not understand right now, but they will eventually watch it later and try to understand. So if they have any question, they can definitely reach you, right?
Yeah, sure, no problem.
Yeah. So thank you.
My response rate is usually I either respond very quickly, like the same hour or the same minute, or it might take a few months. I've got like a stack of emails. If you get in just at the right place, and it's like, yeah, you're there, you're through, fine. Go for it.
Okay, so thank you, Dr. Heinz. We are already running out of time, so we actually schedule 1 hour, but we are almost 1 hour past 15 minutes. So
yeah, no, sorry about that.
It's okay, no problem. Thank you very much, sir, for your time, and
Pleasure.
definitely would like to invite you in our future events. I'm sure you would like to help us to improve our community and be a global community. So we'll definitely want you to invite in future. So thank you
very much. It's a pleasure.
Thank you, and warm welcome from Bangladesh.
Thanks very much. Maybe one day I'll actually be able to get there physically, but until then, I really enjoyed and handshake from Crete.
Yeah, you live in a fantastic place. I just googled the Crete. It's really beautiful, and I would like to go someday in your place. Yeah. Fantastic. So when we'll do a physical one, I mean, maybe in future, so we'll do a large size physical conference. I'll definitely invite you.
Yeah. Thank you very much. Appreciate it.
Okay. Thank you very much for your time.
Thank you very much. Thank you.
Bye-bye.
Bye-bye.